Assume it started. All right, everybody. Welcome back. The numbers are dwindling. Homework must have cleared everybody out. Either that, it's too cold to go outside, and you've got it on YouTube. Either way, I'm fine. I'm fine always. I'm fine. I don't need anybody's help. No, anyway, just kidding. So, a couple housekeeping things before we start. Number one, because I like you all so much, we're not going to have class Thursday. Yeah, I have another trip I'm going on. This is the last one, though. The last. The last.
That's
What?
awesome. I was going to ask if you wanted another one. I mean, class is good.
No, I figure you guys don't need to hear me talk, so
Yeah, we do.
probably better that way.
So we don't have to be absent, all of us.
No, you can all show up and talk, or you can talk. One of you can pretend to be me, so long as you can put it on YouTube. I think that'd be kind of funny.
Yeah, I'll pretend.
That would be great.
Yeah, which I can do because I know all the names of many distributions I don't understand.
Yeah, this is good. You could just kind of just blah 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 blah. That's
It'll
pretty much.
sound like I am.
Yeah, that's pretty much what I sound like.
Well,
So no, this is one of those last trips. I'm sorry it had to be on a Thursday, but this is the last one. This crazy stretch that I'll hope to not repeat again, and then it's final. Well, you'll have me throughout the rest of the class as planned. Other bit of housekeeping. I see that everybody did their homework, submitted it on time. It looks like everybody did well. Did it seem to work okay for you, mostly?
yeah, I felt like there was at least one thing that I got a value that was like 0.02 different.
Okay.
Than
Which one was that?
yeah. I don't.
Omega?
Was it Omega? Yeah, it was like
Huh.
0.910, and but the program wanted 0.912.
That might have been one that I didn't catch that was the same or close to the same as M+. It's one of those rounding things. So. Okay, good. This time's homework. There's another homework out, but it's not an online homework. This is basically repeat the same process with your data that you have. So let me grab it real quick.
Did you say it this week?
It's due October 20th. So it'll be a week from Friday. So basically, this is you can find this homework file on our website at the very bottom, where the homework section is, under homework 3, and it effectively asks you to do the same process that you did in the homework that we did online, which was start by telling me about the constructs. This should be data that you have, by the way. If you don't have data, you should talk to me. Anyway, summarizing the constructs, providing me descriptive statistics, doing a CFA model that kind of fits with your hypothesized number of factors or dimensions that you have. Yes.
On our own data,
Mhm.
the data that I'm using
Mhm.
was originally used in an EFA,
Mhm.
and we pruned items as we went further. Should I start with the full item count for this?
You can do whichever you like. If you want, you can do. If you start with the final result and you say I have however many factors, that's fine. If you say start with the full, that's fine too. Either way, I think you'll find an interesting story to tell. So, so basically, you're going to do a CFA model at first that looks to see whether you can recapture the dimensionality that you have. And if not, you have to re-specify your model to try to improve fit. All right? So I'm okay with almost any type of model re-specification you'd like to have, including dropping items, including dropping factors. If you'd like to add a residual covariance between items, if you can find a way to make it defensible scientifically, absolutely, go for it. All right? But that's part of the process. Otherwise, you have to call I will say this, if you add residual covariance, whatever your factor is, you have to add the word and stuff, or the two words and stuff. So it'd be like happiness and stuff. So if you add a residual covariance without a strong scientific rationale, and right now I can't think of what that would be, but if you do, and stuff has to accompany it, it'd be the grit and stuff factor, or the I don't know what you're looking for, but so yeah, you went through the steps last time. We sort of, in the homework last time, it just said reduce the items and find a model fitting. The process that I'm looking for you to do here is to look at residual covariance matrices, right? The normalized residuals, if you remember that. Look at the modification indices, kind of get a sense for which items are bad. It may be the case that you fit you try your model and it fits perfectly the first time. I'm willing to guess that there may be maybe one or two of you where that's the case. It may be higher, but I think that would be an interesting case study. It's kind of a focus group here. How many times did it fit the data yet? I mean, just in my experience, the first time, even if you have a well-known scale and a well-known set of people or whatever else, it doesn't always work the same way. So, and then once you're done with that, I ask you to talk about calculating omega again for each dimension, and talking about a histogram of your factor score distribution. I created a function in example 04 that did that at the very end, so you can kind of go through that code. Shada.
I have a question that might be
Yes.
measure specific.
That's great. Please, this is good.
So it's a measure that measures self-regulation
Mm-hmm.
in academic contexts, and then there's within each there's 17 items.
Okay.
And then there's 4 different types of self-regulation.
Okay.
Introjected, internal, external, those different types. So would each one of those be a dimension?
Is that what you typically provide scores on? All 4?
You typically would provide a score on the entire thing.
Oh, the 1. So I would say that start with the 1. If it's something that you've been using before and you give 1 score, try 1.
Okay.
Now, if it doesn't fit 1, then you might want to think about the 4.
Okay.
Because basically, if you're saying each of these is a different type, that would be a rationale for why you try a 4-factor versus a 1-factor.
Okay. And if you do go down the route of the 4-factor, and one of the factors only is comprised of like 3 items.
It's still possible to fit there. It has, you still have the idea for the statistical identification for the model. You still meet the minimum number of items. Technically, you'd only need 2 with a covariance between the factors. So you're still fine. And now, it's not as ideal. You're likely to find that factor has lower reliability than the others, but it's certainly possible.
Okay. Right.
Does that sound cool to each of you? Yeah, so I'm going to let you kind of, I want this to be sort of native to your research area, where you're best able to determine what the key guidelines should be. That makes sense. Because I want this to be relevant to you for how you do what you do. Any other questions or thoughts? So again, this is due a minute before midnight next Friday. I do that 11:59 p.m. because if you say 12 p.m. Friday or 12 a.m. Friday, technically that's like 11. That's 23 hours, 59 minutes, and 59 seconds too early, right? So I guess I could have done 12:01 a.m. Saturday morning, but then you'd probably want the whole day of Saturday to work. I don't want you working weekend on this, so.
So the 20th.
The 20th, yeah, that should be next Friday. Given my struggles with reading a calendar, though, I'm not entirely sure. Other thoughts or questions? Yeah.
Can you talk about the chi-square, if it's significant or if it's not significant?
The chi-square. So this is the overall test of model fit?
Yes.
Yeah, I can do that. Let's grab that real quick. I'm going to grab one of our example files. Can you see this okay? If you get down into our results here, the chi-square to tell whether there's significance is right here. The chi-square itself, this is this test statistic, this is a p-value, so it means there's a hypothesis test being tested. The hypothesis is that the null model fits as well as the saturated model. All right.
So when you compare, like, the question would be, like, if you use ANOVA to compare 2 models, nested models, if the chi-square is significant, you would go with the
Alternative.
which is the previous model.
That's right. So basically it's this. The alternative model is the one with more parameters. If the chi-square is significant, you're picking the alternative over the null.
Okay.
Okay? And so in this case, in the chi-square test where you're comparing, this is comparing your model with the saturated model. The saturated model has 9 more parameters. That's what the degrees of freedom is telling you. And this p-value suggests that you should go with the saturated model. If you have an ANOVA to compare 2 models, let me get down to that part of the slides where I do that. Here's an ANOVA right here. This is comparing Model 4 with Model 1. Model 1 had, I don't remember, had the one factor, and Model 4 had two factors here, right? So the Model 4 has more degrees of freedom, or has fewer degrees of freedom, has more parameters, right? So what you're seeing here, Model 01 is nested within Model 4, or in this case, Model 4 is the alternative because it has more parameters. And it's a little confusing looking at this table. You have to sort of understand, like, it doesn't tell you the number of parameters in each, but this degree of freedom right here is the degree of freedom that model has against the saturated model, right? So this means that there are 9 more parameters in the saturated model than in Model 1, and there are 8 more parameters in the saturated model than there are in Model 2, and because 8 is less than 9, you can say that the Model 04 here has 1 more parameter than Model 01. Right, so essentially the model with more parameters, in this case Model 04, is the alternative model. Model 01 is the null model, so this p-value suggests that you would endorse Model 04. Right, you're saying Model 01 does not fit as well as Model 04.
So in essence, you are saying go with the model with the lowest number of degrees of freedom.
Yes, and lowest number of degrees of freedom for the model. That degrees of freedom is another. It's a silly thing because degrees of freedom is always relative to a hypothesis test, right? And so the fact that Levon or R is spitting out degrees of freedom for each model is really not what I wanted to do, because that's degrees of freedom comparing it to the saturated model. What I really want to see is number of parameters, right?
Yes.
Right. So, hey, Jesse.
I confuse things.
No problem.
Because I'm confused. But chi-square distribution. Is its only parameter degrees of freedom?
It is. Yes. That's right. So when you look at this degrees of freedom, it's implying a chi-square. What's that chi-square coming from? Well, it's coming from the test of this model with the saturated model. That's what's causing it to do. It's a silly thing that it's reporting here. But yes, the model in the ANOVA, the model with the fewer number of degrees of freedom is the model with more parameters.
So let us say that the chi-square is not significant.
Mm-hmm.
It is indicating either models is...
That's right. You're saying that the model with fewer parameters fits as well as the model with more parameters. And when they fit as well as, then it becomes, then you can talk about, since these two are giving you equivalent results with numbers, you probably prefer the one with fewer parameters. Parsimony gets applied then. Does that help? Yep. This is good. What other CFA things you want to talk about before we move on to the wild world of IRT or item factor analysis?
For the homework, do you want us to send the syntax and the results?
Yeah, syntax would be great. I mean, all I need technically is the results, but if you could send the syntax, I would take it, and I would, because I can help troubleshoot a little bit too. But then again, I mean, if your syntax is all, yeah, then yeah.
Hopefully not too
Commenting.
Yeah, no, it's okay. You don't have to comment. I don't want to make it more burden for you. You can choose what to send me. If you want help with the syntax, definitely send it to me. How's that sound?
Yes, sir. Thank you.
Yeah, if you guys, and again, if you want help with the analysis, put a lot of information in. If you want to just get the points for the homework assignment, then I probably won't give you as much, attention. So it's up to you how you want to do this. If you want more help, you put more in. I will read it more thoroughly, and I will work with you on it. Does that sound fair? Cool. It's one of those delicate balance things that in grading papers, it's always tough in grad school because some people are there, they just want to get the grade, and I get it. I understand that. And then there's some people who are there who are trying to get the knowledge. And so it's like, so if I spend all of my time on like harassing someone who's just trying to get the grade when they satisfy a minimum competency, fine, check, all right, move on. But for those of you who want to get the knowledge, I'll probably be more intensive. I won't necessarily take off more points, but I might certainly be more, like if I read a sentence that you say and it's not quite right, I'll probably put a comment on it or something like that. Talk about it. Okay. I think Word files work the best, although I'm pretty much open to any other format too if you want. If you're playing around in R, you can send me a markdown file if you want. I don't have a problem. But I don't expect it. Just words cover the minimum for me. Mayumi.
I have a question to the class that
Yes.
I had hard time accessing the homework website.
Oh, when was this?
Like sometimes I could not open because it says Safari cannot open because the website is too busy.
Uh-oh.
So I had to clean cookies and everything to get back.
Send me a note when that happens. I need to know what the load of the server is. So the interesting thing about this is the first time that, so we've got our class on the same server that Lisa's running her class. And I need to see when the homework dates are for each of us. Because if everybody's doing the homework, and I know her deadlines are on a minute from midnight on Fridays also, then maybe I'll just stagger it.
But
You know.
if anybody else,
Was it Monday?
okay, then it's a Monday meeting.
Okay. Well, if you do find, but even if it's just you, if anybody finds this problem, send me a note. I don't know that I can easily fix it. It's a shared server for the website, which makes it cheap because we're paying for it out of pocket. But at the same time, you know what I can do to fix it is to make sure that our homework dates aren't aligned, so there are fewer people who are on there. I mean, that's one easy fix for it. It does seem like that for each one of our classes by ourselves, that it can handle. In our previous experience, when she runs this on her class of 15 or 20 people for one semester, it seems to work fine. There may be just a capacity that we're running into this year for summer. It's the first time we've gone up to this level. Thank you for bringing that up. And I apologize if that does happen. I know it's frustrating, but what I will tell you is if you're in a situation where it's stuck and you just send me a note, we'll fix it. It'll just, you know, the deadline, we'll move the deadline for you. It'll happen.
I just want to figure out if it's my problem.
Yeah, I know. I hear you. Yeah, no.
Or everybody else.
Here, let me give you my impression of it. Normally, when someone asks that for something I set up, I know it's my problem. So I don't think it's your problem. I can't imagine a way that Safari would tell you that unless it's actually probably being true.
I will figure out. Yeah.
So yeah, and again, if you're I ask your patience with this because it's a shared serving place, and I know my website breaks sometimes when a lot of people are on it, and it's sort of this weird spot that we're in. The university won't give us, so the homework system is built on an older framework that uses Microsoft, and the university won't. Well, they'll let us have space for it, but it's going to cost like $1,000 a month or something like that for us to pay for it. And so the server I'm buying out of pocket is like $10 a month, right? So yeah, I can pay $10 a month. I'm totally cool with that because it certainly helps. I feel like helps the class experience and it gives you some practice. Totally fine with that. But this is sort of the problem with it. Like to scale up from it, it's a little bit harder. But I appreciate your help. But if you're ever in a spot where you're doing that and you're coming up on the deadline, shoot me the email, and I will fix the deadline. It's easier for me to fix the deadline than to fix the capacity of the server.
Okay.
So I know it's not ideal, but that's me, and I broke. Anyway, I've broken too many things lately. I have very low self-confidence when it comes to tech right now for some reason. I don't know. Although I'm always amazed when I get the tech to work like the first time here. I'm like, oh, this is going. Other thoughts or questions on CFA? Yeah.
Quick question about and maybe you already addressed this, and I apologize. It's late, but we had to do the item analysis as far as means and standard deviation and all that. Are we going to be asked to replicate that in future assignments?
Just right here, question 2 wants a little bit of descriptive statistics. And it talks about mean, standard deviation, minimum, maximum, and the item total correlation. So effectively.
So for the first homework, I was able to manage that through SPSS.
You
When I
can do
tried
it.
to
Oh, sorry.
run the analysis data function in R, it said it's not available for the current build of R.
Weird.
Yeah.
Send me that email. Send me a note with that if you run into it again.
Okay.
But if ultimately for here, for this question, since this is on your own, if you want to do an SPSS for this question, it's fine.
Cool.
You could also use M plus or whatever. The means and standard deviations are pretty standard to compute, so totally okay with me.
Okay. Thanks.
You're welcome. Thank you. Okay. I do not want a numbered list from you. So, in all truth, I read this from Lisa. I borrowed this from Lisa, and yes, I do know. Try to write this like a traditional results section. Is what I'm going with, right? A results section in a journal. It doesn't have to be super traditional, but just sort of these 5 bullet points here are what to include in the results section. And it's sort of going to, it's not going to be exactly a results section because nobody would write a results section as long as you're probably going to write this one. So, but you can make it short. That's fine too. Okay, are you ready? Ready to start? This is a good day because we're going to get into measurement models for categorical data. And so the whole time we've been talking about CFA, I've been saying, hey, just remember Likert scale, probably not continuous. Yes, and I know there's a paper that was out that said 5 categories, probably not continuous. Right? Actually, I saw the authors of that paper at my conference. The reality of it is the continuity assumption really has ramifications for how many test scores you have. And we saw this on the factor score plot last time. I can flip back to it at the end here. If the data were truly continuous, you wouldn't see this upper limit up here, right? So here is the ceiling and actually floor, right? The reason the ceiling and the floor exists is because everybody at the ceiling for one of the factors is picking essentially the maximum number of that Likert scale. It's rescaled onto a factor score distribution. I wanted to try to compare and contrast. I'm sort of going off the cuff here, but I'm trying to compare that factor score plot from the simulated data with the real data to try to make a point. There it is. Okay, so here's the simulated data. All right, this is simulated data assuming that the factor or the data were truly continuous. Like I generated them from a multivariate normal distribution using the multivariate normal distribution assumption. And you see this scatter plot. There's no ceiling or floor. And the reason for that is they meet that assumption of CFA. They're generated, they're truly continuous. But here's the reality of the data right here. Right? You see this bound to it. And that's what we're up against. Right? And so, yes, it looks largely the same. One versus the other kind of look the same, but really what we're up against is this assumption of continuous data. And there's a set of cases where you can take Likert items and be mostly okay, probably. Mostly, maybe, probably, maybe not, whatever, when you switch over and you do a CFA with it. But by and large, to me, I think the bigger issue is that most of the time doesn't ever hold in reality, right? So when you see things like a ceiling and a floor on a continuous factor for a CFA, that shouldn't be there. That's a consequence of your categorical data. How much of that does it impact your results? Well, again, that depends on the shape of the data. For the data to fit the CFA assumptions, it has to be normally distributed because the normal factor with the normal residual variance is provided as a kind of a pass-through of normality. So each item has to sort of look normal. What's that look like in a Likert scale data? Let me see if I can draw this. Well, it would look, if you had like item responses 1, 2, 3, 4, and 5, you would expect a histogram of the proportion to be something like this, where it's somewhat symmetric, unimodal, right? No zeros anywhere, stuff like that. You ever find that in your data? Probably not.
Every single time.
Every time. So this is why you should be. This is why we're all expecting you to do great things, Craig. When you're.
Or this is why all of Craig's papers will be redacted.
That's a good point. I followed what you did in this example where everything was great. I don't know what the problem was. All right, I generated the data. So in thinking about this and thinking about big picture statistics, what we do in a lot of statistics when we have non-continuous data is we just switch the distribution of the data. In regression, you saw this. We went from linear regression to, if we had a categorical item or a binary outcome, like a dependent variable, we'd switch to logistic regression. Well, that's what today and the next couple lectures are going to be about. When you have binary responses for your items, so they're 0 or 1, and that could be yes or no, or however you want to recode them, correct, incorrect. We're going to switch CFA's assumption of normality to logistic regression. All right? Logistic or probit, some type of version of regression that involves binary responses. But moreover, that fits into a bigger picture. So when you get into that, it sounds pretty straightforward. Like in a CFA model, when we wrote down the equation for each item, remember there was a series of equations, and they were all regression functions, right? It was like in that example with the 6 items, there were 6 regression lines, and each was prediction by the factor. Now, if all those 6 items were binary, it would be 6 logistic regression lines. But the factor is still going to be treated the same way. We're still going to have, once we collect it, once we get it, we're going to talk about its reliability. We're going to want to use it in a structural equation model, or we want to use it to predict something else, or we're going to want to give some people scores with it. So, getting into this, let's remember the big picture of classical test theory. It predicts the sum score, right? Your sum score is your true score plus error. In this case, because it's a sum, the items are assumed exchangeable. Whoops, that thing right there. And their properties are not part of the model for creating latent score, right? Each of the items contributes the same amount of information to the test score, and that's what you know. Because the latent trait estimate is the sum score, it's very difficult to make comparisons across different test forms. For instance, the item difficulty is the mean of the item. It's sample dependent. The item discrimination, which is the item total correlation in classical test theory, is also sample dependent, meaning it's going to fluctuate widely from sample to sample, perhaps. Furthermore, estimates of reliability in classical test theory assume without testing, now I did show you how to test these, unit dimensionality and either tau equivalents or parallel items for what you do. But the reality of that is that measurement error was assumed constant across all levels of the trait. And this is the same thing that happened with CFA as well. We assumed there was one error for all the scores. If you provided data to all the scores, you got the same standard error of measurement. But we're going to see pretty soon this is going to change. So in classical test theory, how do you make your test better? More items. What type of items? Don't care. More of them. For CFA, we sort of remedied some of those issues. It's a linear regression. We have an outcome that's our score for the item, and we're predicting it based on a regression of a person's factor score onto it. The nice thing is, in this case, that both items and people matter in predicting responses. So we talked about item difficulty. It was our mean of the item, which is really sort of item easiness. I don't know how you want to describe it. And then the factor loading, which is the item discrimination, how well an item discriminates between people at low and high levels of the traits given by that. And both of these, what we talk about, are sample independent, and that's because when we take the factor itself, we're creating a scale for the factor, and that scale is the part that we're trying to normalize based on, right? So if we say the factor follows a normal distribution of 0, 1, that has ramifications for the size of both mu and lambda, right? And because of that, we sort of get a picture of people outside of a picture of the sample. So mainly, if you think of it this way, we've set the scale for the factor. This is our norming group, right? This is the set of, we're saying if it's normally distributed, there's a nice normal distribution. That's the distribution of the people. So how items show up differ depending on sample. But because, actually, so what we were trying to do is this factor analysis is giving us, the model itself implies what the observed covariances amongst items should be. Right? So that's how we go and test our model fit. We say, hey, if your 2-factor model is true, we should see this pattern of covariances amongst the items. And if not, the model must not fit. Right? So, furthermore, we also have this other idea that the items should be uncorrelated after controlling for factors. And we saw at the end of the lecture and maybe at the end of the homework that we actually could violate that in CFA by adding a residual correlation. And that was great. But ultimately, this idea of local independence basically says that the factor is the only thing causing these two things to covary is really important. And so that residual covariance is a way around local independence that weakens your argument about what the factor really is measuring. So that's why I tell you to add and stuff to your factor. Although if any of you can get that published, I'll give you $100. Just come back to me in your life and be like, hey, I published a paper that said the factor name and stuff. Like if you put it in the title. Happiness and stuff is measured in. That would be awesome. I don't think it. Does anyone think that could get through?
How about a poster?
Oh, see, the poster. I think you probably could.
Yeah, it's still
That would be
published.
cool. I'll give you $5. A poster or a conference talk, an actual presentation would be 10. But like a published peer review article, let's go with 100. I don't even know where these numbers go. What's that?
That's a low price.
I know.
You gotta make it a little bit higher.
No, I don't have that much money. That's the problem. Busy spending it on servers.
I'm sorry.
That's right.
Do you have an impact requirement?
No impact. Yeah.
So just to make sure I have this right, so local independence is the argument that the factor is the only thing that is counting for the observed covariance.
That's right. Yeah. So, and again, the way I think about it is, if I can draw a picture, this is always dangerous. Remember that when we saw it with two variables x and y, if they're correlated, we thought that was because either x predicts y, y predicts x, or something else predicts x and y, and that factor is really taking that form of the something else here. X, y. All right. So this is the latter thing right here. That's what local independence is saying. Good question. Okay, so because we have the individual item responses, what we can note is that we were able to have items vary in discrimination. Items also vary in the difficulty. They also vary in the amount of information they carry about the factor itself. Effectively, your standardized loading, although it's usually quantified a little bit differently. So if you want to make your test better in CFA, you need more items, but they need to be better items. Uh-oh, I just lost my pencil. Come back now. More items, but also better items, as it says down here. Okay. So, but also, one other thing that shows up in CFA is that measurement error, once you provide a factor score, the error for that factor score, the standard error of measurement, is the same across all the items. And the reason for that is because of this multivariate normal assumption. When you get normal factors and normal data, you say the data are normal and so forth, normal factors, normal residual variances give you the assumption of normal data. But in multivariate normal distribution, variance, which is usually thought of somehow related to error, is independent from mean, which is usually thought of as factor score. Right? And so when you have that separation, you'll only get this one constant value of measurement error across the trait itself. So I've lost the pencil now. So there goes. Start do this. All right. So if we go from CFA to IRT and item factor analysis, we start to see a little bit different. So over here on this table, we have the type of variable that you're trying to predict. And you can either have continuous data, which was what we saw before, or discrete or categorical. We sort of use those terms interchangeably. And if in the types of analyses that we'd have before, we could either have observed predictors or latent predictors, right? Observed predictors is like regression. So if you have continuous data, continuous outcomes, and an observed predictor X, that is like linear regression, right? Right here. Hey, I got it back. There it is. Okay. If we had a latent predictor, that was a confirmatory factor analysis. So latent predictor, continuous data. Well, observed predictor with discrete data, that's where we would get into the case of logistic or probit or multinomial regression. And the latent predictor is in the same discrete or categorical data, gives us names like item response theory or item factor analysis. So this is like you remember those the analogies questions on the GRE? Mm-hmm. CFA is to linear regression as IRT or IFA is to is to logistic regression. So the basis for IRT and item factor model comes from these ideas of generalized linear models. So I don't know if you've seen this before, but when you took regression in ANOVA, that was something called the general linear model, and in fact we've changed our curriculum to even call 810, EPSY 810 general linear models, right? So it's regression and ANOVA combined. When you switch the data out, and because it came later, they're like, oh, what are we going to call it? That's where the "ized" came. These are generalized linear models, meaning they're still general, but they apply to all different types of distributions of data. Right? And the same thing works in measurement. Right? So the way I like to think of it is that if you can dream it up, if you observed everything, you can dream up a model for it. There's a measurement model that works the same way. Right? So it's not just for discrete and categorical data. If we had other data out there, we could do that too. So we're going to review a few concepts from the generalized linear models. And here's the big thing. I like to think of it this way. Okay. So over here we have data. Right? So there's three parts to a generalized linear model. Right? We have some type of distribution of the data. We have something that transforms the mean of the data. And then we have something that deals with theory over here. So this is transform. So the data themselves, right? So you may have normal or non-normal. In a generalized linear model, the straight standard normality assumption is part of that as well. You may have non-normal, and it's conditional distribution of responses. What do I mean by conditional distribution? I mean the distribution of the response once you've conditioned on all of the predictors, right? So in regression, as I mentioned to us in class, we're not saying the data are normal. We're saying that once we predict the data, what's left over is normal, the error, right? The conditional distribution of the data given the x's. And same thing with the generalized linear model. So you have to pick a distribution, is what I'm getting at here. Right? If you've got binary items, there's a distribution for that. Jesse, what distribution works for binary items? I'm not picking on Jesse here because he's in a math class, like an actual math class.
For binary items?
Yes.
You could use binomial.
A binomial. Another description of a distribution for binary items, a binomial with one trial, right?
Bernoulli?
A Bernoulli, that's right. So the terms that we usually think of for binary items is binomial and Bernoulli. I realize my writing is bad. This is a Bernouilli. So Bernoulli is so if you remember the binomial distribution from like basic stat, it was a distribution we used to characterize the number of successes out of a set number of trials, if each trial had the same probability of a success, right? So it's like how many times would I roll a 3 on a 6-sided die if I rolled the die 10 times, right? That's what this distribution is trying to tell us. The binomial is with one trial is like a binary item response, right? So if I have this 6-sided die, I'm going to roll it once. What's the probability of rolling a 3? It's 1 divided by 6. It's a fair die. The Bernoulli is often used to characterize that. A one-trial binomial is also a Bernoulli, but either way, absolutely appropriate. Sorry, not to tell you. Jesse is not wrong. So you may hear either, depending on who's talking about this, and that's
Just assume that n was equal to 1.
that's exactly it. I'm not trying to correct you. I'm trying to add to it. So yeah, and I'm teasing you back. So I don't know if I'm teasing you back, but I'm not trying to make sure that I'm not like picking on you too bad. All right. So the next thing is we have to somehow do something to the data, because if we were trying to predict the data themselves, we want the theory. Our linear, actually, let's go over here to this right-hand side. The linear predictor of fixed and random effects. That's what we put on the right-hand side of the model equation, right? So it's got usually an intercept, some type of regression slope times the thing that you've observed, which is what we call a fixed effect. The regression slopes we call fixed. Sometimes we have random things there. The factors themselves are random. The factors had to have some distribution to them. That's what makes them random. Anything where we say factors were distributed normal 0, 1 or something like that, that makes them random. But over here it's the regression line. But we know with the regression line, because of the way things work, if the factors can be continuous, then the line itself has to allow any real valued number, right? So on the right-hand side, what we're making predictions of is going to go on the whole number line from negative infinity to positive infinity. Sometimes we call this the real number line. But the problem with data is that what we're going to predict, which is often, and just like in regression, we're going to predict often the mean of the response, the mean of the outcome. What is the mean? What range does a mean of a Bernoulli or one-trial binomial have? 0 to 1, right? Right? If all the numbers are 0 or 1, then the mean of it can't be outside of 0 or 1. So the mean over here, which we often describe as p, exists on the interval of 0 to 1. Right there. Right? So we have a disconnect. We can't link this entire interval of what we want to put our predicted response, we have to somehow, sorry, what we have to do is link this interval of our predicted response so that negative infinity maps onto effectively a 0 and positive infinity maps onto a 1. And that's where this link function comes in. It's a transformation that we apply not to the data. We're not transforming our data at all. We're transforming the mean of the data and then predicting the mean transformed response. Right? So in this case, with a binomial or Bernoulli, again, P is the probability. That's the mean. One of the more common transformations that we find is something called the logit, which we're going to see in just a minute. L-O-G-I-T. Right? So the logit of the probability itself, now the logit is the log, the natural log, of P divided by 1 minus P. I'll have a little bit more definition about that in a few slides to come. What this ends up doing is it maps the mean onto the space of negative infinity to positive infinity. And so now, because the mean can be any of those numbers, we can predict it with the linear predictor itself. Yeah, Jesse?
So is the link function a transformation?
It's a transformation, but it's not a transformation of the data.
Right.
It's a transformation for the mean itself.
But like just like linear transformations in linear algebra, like is it 1-to-1 and onto?
It's not. God, it's been a long time.
Yeah, I don't remember what
it's not necessary. It's not a linear transformation. Let's put it that way. It's a non-linear transformation.
But something similar where for every input there should be an output. Absolutely.
Every unique value on the linear predictor will result in a unique value of the mean itself. Yes. So maybe that's what it's looking for. So there's certain other things that linear transformations have, like in terms of scale and variation, and so other things that don't show up here. But yes, every value that you can come up with predicting a number will have a unique value represented on the transformation as well. Okay, so how does this work for binary outcome? Let's imagine this. Let's say you have a single. Yeah, Shada, sorry.
No, it's okay. So for the linear predictor part on the previous slide,
Mhm.
so you said that the factor is random, but then is the intercept and the error fixed?
No, so let me give you an example of this real quick. So if we were going to do, like, let's take an item. Let's take, we'll call y as our item. It can either be 0 or 1. So let's call P the probability that y for a person and an item equals 1. Right? So that's the mean, effectively, right? And what we're going to do is we're going to take the logit of P and predict it. And we're going to predict it with the similar type of CFA function. Right? So we may have mu for an item plus lambda for an item times f for the person. Now, error is a little bit more suspect, because we actually, for these models, we're going to see that error ends up going away. And I'll tell you why in just a moment. Basically, this is what the linear predictor looks like. And actually, the linear predictor, if you think of what we were doing in regression, to make a prediction, we never included error anyway. Right? So it was always the part that wasn't error. So this is the linear predictor part itself. So yes, even though the factor looks like this thing is normal, 0, 1, so the factor itself is a random variable, it still all works the same. Does that make sense? So we're going to estimate values of the mean. We're going to estimate values of lambda I. Because we're not giving them distributions as well, we call these fixed effects.
Got it. Okay.
So what I'm blurring the language here from, if you've taken a multi-level class or a hierarchical linear models class, there's a set of models out there that are used when you've got similarly clustered data where you have to have essentially random effects show up in the model. One of those is like a factor model where we turn off this we let the factor loading equal 1. And then what the factor represents is essentially a person's random intercept, right? You have an overall fixed average, and then how much a person differs around that is given by their factor itself. So that's where that term starts to get confused from. But just for us right now, it's just still the same factor that we knew and loved before.
Okay.
It's just now predicting data that aren't. It's predicting this weird transformation of a mean. Thank you. Other questions? Okay. Where did my play button go? Slideshow. There we go. There we go. Okay. I love how I ask my iPad these questions. Like it's going to. I need to phrase it with a "Hey Siri, how are you today?"
I'm happy. happy to be alive.
So am I. Okay. It didn't show you Siri, though. Evidently, when I do that, it doesn't work. Anyway, so what we're talking about, let's imagine we have a binary outcome here. What we're going to do, the conditional mean, we're going to predict the mean, right? There's probability. And if we didn't do a transformation to it, if we just plug that mean into the regression, what we would end up getting is the predicted probability of a 1 plus error. And what we end up seeing is the linear regression will quickly go out of bounds, right? Regression values of 1.2 and so forth. Speaking of, by the way, there's an R package that I used this summer in a workshop I taught. It's an R package for diagnostic models, and they don't do things the right way. And it gave me a probability of 1.2 in front of my class. I thought that was really funny. Embarrassing, but funny. So this is like what happens when you use someone's R package who doesn't know what they're doing. Right there. But let's hope that that's not the case. Anyway, this is bad, right? We want it to be bendy. We want the line to shut off or to asymptote at a probability of 1 or an upper probability of 1 and then a lower at probability of 0, right? So we need this non-linear relationship, and the first idea that we could come up with is to transform that mean probability into an odds ratio. If we took the probability divided by 1 minus the probability. Now, how many of you have looked at or had logistic regression before? Like very few of you. Okay, so this is the weirdest part. The logist part of the logistic regression is the craziest thing. When you take something that's a probability, we can create odds out of it. What are the odds, right? Let's think of it this way. What's the probability? Let's say I take a coin out of my pocket and I want to flip it. It's a fair coin. What's the probability it lands on heads? 0.5, right? The odds of a head is sort of the relative size of the probability of having heads to the size of probability that's not heads. So that we do that, we take that by probability divided by 1 minus probability. So 0.5 divided by 1 minus 0.5 gives us an odds of 1, which means we have an odds of 1 means there's an equal chance of the event happening or not happening, right? So what are the, if I were to say the odds KU's football team is going to beat Iowa State this weekend, is that an odds of 1? No. Where's that going to be? Less than 1, right? It is. It is. It's a building process. I feel I'm not trying to rip on KU football because each person who's working out in that building down the hill right there is busting their tail and putting their life on the line really to do better. So I'm not trying to pick on the children who are playing and the coaches who are coaching them. I think they're probably doing the best they can. So just not picking on them. I'm trying to describe odds where we typically see them, which is in gambling, right? The odds of an event. If the odds are really low, if the probability is really low, the probability KU's wins is like 0.1, then it'd be 0.1 divided by 0.9 or whatever that is, 1/9, right? That's a very low odds of that happening. The flip of that is, the probability Iowa State's wins, 0.9 divided by 0.1, it's like 9, right? So it's 9 times the likelihood of Iowa State winning over KU State winning, or KU State, KU winning. God, I can't even talk. So, but the problem though is that odds ranges from 0 to infinity, right? Because you can have a 0 probability that leads to 0. The odds are 0. And the flip, if you have a probability of 1, then you get 1 divided by 1 minus 1, which is 1 divided by 0. Technically, that's undefined, but it approaches positive infinity as the probability gets to 1. So that's still not helpful because if we're trying to predict the odds, we still are bounded. We're still half the number line. We need the whole number line. And the way that we do that is to take the log of it. And this is the natural log. Many of you in math back in high school used to call that ln, but now we pretty much just use log for everything. The log, I guess the base, we call that the base of it. The natural log, it takes the log of this number. So any number that shows up, any probability, any odds that's at 1, the log of 1, you remember what the log of 1 is? 0. Right? So the log, if you have a 50-50 chance of something happening, the log of that odds is 0. Or so the logit for it is 0. And that's what this right here happens to be. The probability of 0.5, take the log of the odds, you get a logit of 0. The log of the odds is called the logit. I swear I don't know the derivation where the word logit is, but it makes me want to make the terrible pun, which is how do you fix an odds ratio to make it continuous? You log it. Oh no. Never mind. Terrible. The pun. The other thing that we talk about with logits is that there are sort of reflective about 0.5 for probability, meaning that take a look at here. If we have a probability of 0.1, the log odds associated with that is negative 2.2. Now 1 minus that, or the complementary probability of 0.9, its log odds is now 2.2, right? So you can see it, the complementary probability provides you the logit with negative 1 times that value. So if you wanted to think about it, the probability of 0.99 leads to a logit of 4.6. So the complementary probability of 0.01, what would its log odds be? Negative 4.6, right? Negative 1 times that number. So the reason why I'm talking about this and going into this is that all of our IRT models, for the most part, are on log odds scale, right? And it's this somewhat artificial scale that seems to be weird, but this is how it sort of corresponds to probability. If you see a log odds of 4.6, you know that thing is likely to happen. If you see a log odds of negative 4.6, that thing's unlikely to happen. If you see a log odds of 50, right? That's 0.99 with like 9s all the way out for 100 spaces or something like that, right? It's really close to 1, right? So the log odd, the difference in probability from a logit of 50 to a logit of 4.6 is effectively 0, right? I mean, it's negligible because of this asymptote.
So did you say that a log of 1 is 0?
The log of 1 is 0, yes.
So then...
So the probability of 0.5, we first have to convert it to the odds, which gives us the odds of 1,
okay.
and then we can take the log of that. Yep.
Okay.
So it's the probability of the log of the odds of an event happening.
Yeah. Okay.
It's like a double transformation,
It's
if you will.
deception.
It's like what? Deception. Yeah. Kind of.
0 like basically equal chances.
That's right. Exactly. So yeah, right here, if you get a logit of 0, it's like equal. Exactly. Right. So everything that we're going to see is like regression on this imposed metric right here. So you can see there's a nonlinear transformation probability. This is a graph that talks about the probability on the top and the logit on the bottom. And you see a probability of 0.5 gives us a logit of 0, but as you start to go up in probability, then things asymptote in a certain way. They shut off. So the other thing that could happen, that could go wrong if we used just our typical normal regression model for binary outcomes, is that the error, if we wanted to throw error in it, would be very obvious, right? There'd be 2 values for each person, right? It would either be 0 minus the predicted probability or 1 minus the predicted probability, but either way, there's sort of a fixed value in that range, meaning the errors can't normally be distributed, which is a problem. So the other part is that the mean and variance are dependent. So here, take a look this way. For a binary variable in the Bernoulli distribution, the mean is p. The variance is p sub I times 1 minus p sub I. It's a function of the mean. So what does that mean? What is it? Yeah. It means if you know p, if you know the mean, you know the probability, you automatically know the variance. Now compare that with a normal distribution, right? What's a good normally distributed variable? I don't know. Height. If I tell you the mean height, let's imagine height's normally distributed. It's probably not, but let's imagine it is. Let's just go with that. If I tell you the mean height is, I don't know, 67 inches. I don't know what that means.
Why is the number?
I don't know. I'm just pulling numbers out of the air now. What is the variance of height? No idea, because the mean and the variance are independent, right? And so that's a big key. If I tell you the mean probability that KU is going to win, if KU played Iowa State 100 times, they would win, let's say, 1/10 of those. So the probability of them winning is 0.1, was the variance in them winning. It's 0.09. 0.1 times 1 minus 0.01. Or 0.1, sorry. 0.1 times 1 minus 0.1. Right, which gives you 0.9. 0.09.
So you look at the mean, then you get the value.
Yeah, that's right. That's right. So the main thing is, the issue in statistics, though, is that a lot of the parts from the normal distribution that depend on the variance, it plays a large role in a lot of things in the normal distribution. It plays a large role in our linear models, for instance. It plays a large role in figuring out what the standard errors of these terms should be, and so forth. So if we, if we have this dependency of mean and variance, then what we're going to talk about with each of our parameters is going to change. So how do we solve this, though? And that's where I love that $. That is an expensive y right there. That should be the mean. That should be y bar. All right, this is the normal distribution up at the top. This is a picture from Wikipedia. The Bernoulli distribution is down here at the bottom. It tells you it's going to tell you the probability of a response. Right. So so this graph over here gives you a bar graph. The blue line is for a probability of 0.25. Right. So the probability of a 1, this is a 1. The right hand side is a 1. Is 0.25. Probability of 0 is 0.75. That's what this is telling you. But this is the distribution that we use. We swap out the distribution. Well, everything else that goes with that, like this function, everywhere this goes before, now we replace with the Bernoulli PDF. The PDF is called the probability density or probability mass function. Where it shows up in what you do this is what's generating the likelihood function. This is what's generating our log likelihood. Because what we do is we plug in all of our parameters, we get our predicted values, we plug in our data, and from that normal distribution, we'd get a height for each person. We take the log of that and add that together. That's our log likelihood. Now, in the PDF for Bernoullians, you have this nice normal distribution, but instead we have this. If a person gave us a 1, this is their height. If a person gave us a 0, this is their height. Okay? So it sort of gives us a different distribution function. But everything else sort of works the same for the way the process of likelihoods work. So what we're trying to do now is predict the log of the odds of a probability. Now I'm defining this probability almost exclusively to be the probability of a 1 for a result that could either be 0 or 1. Now you note, I could have decided to choose to define the probability as the probability of a 0, right? And that would be fine too. You sort of have to make a choice. The nice thing is the results are complementary as well. There's a certain reflection that happens in going from 1 to 0, and vice versa. Right? So this is what happens. This function right here is called our link function. Right? But we can actually go back. Once we do this, each one of our parameters, beta 0, beta 1, beta 2, are on the scale of logits. Beta 0 represents the average or the predicted logit of a value of 1 when x and z are equal to 0. What does that mean? Right? If beta 0 was equal to 0, so we get an intercept at 0, that means when x and z are both 0, our predicted logit would be 0. And so, yeah, that's exactly it, right? We could back translate that logit. If you look at this graph way over here, logit of 0, back translate it, we get a 0.5 probability. We could also back translate it to a log, or to an odds. Right? How would we do that? We take e to the value of the parameter, we get the odds. So e to the 0th power gives us the value of 1. Right? How do we get the probability? We take e to the predicted value over 1 plus e to the predicted value. And so what this gives us is e to the 0 over 1 plus e to the 0, which is 1 over 1 plus 1, or 1/2. Right? So we can always go from logit to probability, because probability is understandable. Logits are crazy. Odds are crazy, right? Who thinks in odds? Very few people. Wait, do you?
Well, no. We have a paper where we use logistic regression and use exponent beta.
And that's exactly it. The odds. This is talking about a lot of logistic regression describes effect sizes in terms of odds or increases in odds, and that's exactly what happens.
When we added 1 to the denominator, like we wanted to confine our results between 0 and 1, right?
Right, that's right.
So we added 1.
That's right. The one down here, yeah, that's effectively it. What we had to do to sort of identify this is we had to zero out all the parameters for one of the options, right? So this could either be 0 or 1. We picked the 1 side, which is this side right here, and the 0 side got a 0 everywhere. And so e to the 0 is always 1, effectively. So how are we doing by this? Is this starting to... It's sort of abstract. Once we get some numbers, it usually helps. Now there are... Yeah?
Just to confirm that the 1 in the denominator can be exchanged with 0?
No, where this is coming from is like saying e to the 0 over e to the 0 itself.
Oh.
Right? So what this is effectively is saying is you're taking e to something over e to something else. So that's where that 1 is coming from. It's not... It'll become a little bit more apparent when we get to the multi-category models for why that is. But for right now, it's just a 1. So another way we can conceptualize this is through what we call latent responses for binary data. This is really more, sometimes I like to call this, I don't like calling this latent response. I sometimes call this underlying. So think of it this way. Let's imagine for every binary variable that we have this distribution y, we have this variable that's continuous called y star. All right, that seems a little weird. That's sort of what happens. What happens is if y star is bigger than some type of threshold, then the response becomes a 1. This underlying distribution is kind of thought of like a propensity distribution or something that would be someone's likelihood of being a 1 for this item or this piece of data. And so there's some cut point where if that underlying value goes above the cut point, they give you a 1. And if they go below that cut point, then they're giving you a 0. Right? So when we do that, we can actually conceptualize this model just like this. There's a threshold value, there's your model value, and there might be some error. And the error term, so again, this part over here is your linear predictor, but the error term itself, we can actually conceptualize this as following something called a logistic distribution, which is the craziest, one of the craziest distributions out there. But one of the things is that the variance itself is often given by something called pi squared over 3. What? That's like stat trivia, right? The variance technically, the logistic distribution has 2 parameters, mu and s squared. But the variance is actually pi squared over 3 times s squared. So we often just call the variance 1 to make it. It's not, this underlying variable does not exist. So we don't really have a mean for it. We usually set this to 0, and we don't have a variance, so we set that to 1. And when that happens, the variance becomes 3.29. This rarely matters itself. Okay, but this is it. So the thing about it is that logit function was a transformation of the mean that did the job of mapping this continuous, or this value, that the mean that goes between 0 and 1 onto the continuous real number line. There are other transformations that people use as well. There are other link functions, is what we call them. One of them is something called a probit model, which sounds terrible. What is a probit? Well, it's a link function that takes the mean and converts it into a number that's on the continuous number line. But the way it does it is it uses the z-score that comes from the normal distribution for it. You remember the cumulative normal distribution? Remember that from basic stat? You had the cumulative normal is the probability of being at or below a given value of the distribution itself. So if I switch this over here, or draw this, whoop. I want a pen. There we go. This one. If I were to draw this, right? So if we have this normal distribution, there we go. It's almost normal, right? The cumulative probability is the area under the curve that's to the left of a given point, right? So the cumulative distribution sort of looks like this. Sometimes we call this an ogive. Right? This is an ogive function, which I don't know. Hey Siri, define ogive.
A pointed or Gothic arch. Do you want to hear the remaining one?
Yes.
A cumulative frequency graph.
Cumulative frequency graph. Okay, so the ogive function is telling you the probability associated with x. This is the probability of any value of x less than or equal to this x that you pick, x star, we'll call it right here. This is less than, right? So the probability that happens to be, it comes from an integral, you know, because it's giving you an area under the curve. But this probability, again, for a probability of 0.5, it's like saying, where is 50% of the distribution below? And we know with a normal distribution, that's below the mean, right? So this thing right here would be the mean. So this is what this ogive function is doing. It's telling you for every one of these probabilities, it's going to convert them to something that comes on a normal scale right here. And this normal distribution down here follows the real number line. So what we do often is we don't call this x, we call this a z-score. What's a z-score? It has a mean of 0 and a variance of 1. Right? So that means when we say a probability of 0.5, that translates into the probit link transformation gives us a value of 0 on the probit scale. Yes.
So why probit?
Why which one?
Yeah.
It's often been a matter of discipline-specific taste. So in economics and some political science, I think probit gets used a lot, and that's sort of where it started. In statistics and other places, you'll see kind of equally. In item response theory, logit I feel like starts there. And oftentimes there's a couple mathematical quirks that show up when you do one thing with probit when you don't do logit or vice versa. So the reality of it is one is easily obtainable. They're almost approximately the same with using a scaling constant. The logit is 1.7 times, sorry, the probit is the logit is 1.7 times higher than the probit, right? So if you take 1.7 times all the logit values, you get the probit back. It's the other way around. I'm trying to think which one's higher. But anyway, so you can pretty much always transform between the two, but it just shows up sometimes for how it works. So again, this is pretty much no, do that change. I can't get the slide to change. Oh. The biggest problem I have in all the Mac stuff is all the Microsoft products, which is the biggest problem I had with all the Microsoft things. All right, we're going to kill you, PowerPoint. Start all over again here. It's really funny. It's like, no, I'm not leaving this slide. I'm not leaving it. No, it would just shake in place and do whatever.
They need to know more.
Yeah, no. Oh, now it's drawing with my pencil, with my finger instead of the pencil. There we go. So probit versus logit, should you care? No. If you're building an algorithm, like for instance, I'm building an algorithm, there's this nice stat thing that probit gives me that it's harder in the logit, I care about that. If you're not me, probably don't care. Yeah. So, there we go. So, now, back to our measurement class for the last 5 minutes. How these types of models are the same as CFA. Let's go through that. In the IFA, item response theory, item factor analysis. By the way, I'm going to use these words interchangeably. If you come out of a psychology-based tradition, you typically use the word item factor analysis. Although I feel like in recent years, this has really started to be downplayed, and we usually just call everything IRT. So depending on where you are in your lineage or whatever, you might call it item factor analysis. Otherwise, it's IRT. It still means the same thing. It's like CFA with categorical data, right? The measurement model is where our latent trait estimates depend on both items and people, so just like CFA. Items differ in sampled independent difficulty and discrimination, just like CFA. And then after controlling for a person's latent trait score, back in the CFA we call this F, right? In IRT and IFA we call this theta, which is often denoted by the Greek character theta, which is like a 0 with a flat line through it, lowercase theta. So again, after we control for a person's theta, item responses should be uncorrelated, which is also called local independence. And that's because, again, the only reason the item responses are correlated in the first place is this theta. And if this is unreasonable, we can fit in a multidimensional model, and we can use this to test whether our model fits the data and so forth. But how these fields differ from CFA are somewhat notable. Sort of the nuance of why you'd want to take like Dr. Skrupski's IRT class, which meets, I think, this afternoon. Actually, I think it meets Thursday. Pardon me. Have you taken this class this semester?
Yeah.
All right. Is he picking on me in that class?
No.
Okay.
Not yet.
Not yet. Okay. Well, just checking. I was trying to see how much I should pick on him, but no. I think we're pretty much on the same page on all of this. This is really not controversial. The IRT, item factor analysis, use link functions, the transformations of the mean to predict, right? So we're not just predicting the outcome directly or the mean of the outcome directly, we're predicting the link transform version of it. Let's see here. And it specifies a nonlinear relationship between the item responses and the latent trait. That's where what we're going to see is this what we call an item characteristic curve. If we have theta and it goes from low to high, the probability of an item response given theta is going to be a curvilinear line, just like you'd see in a logistic regression. So it's got this S shape. The errors can't have constant variances across theta or be normally distributed. So what we'll end up seeing is that most of our models will not have residual variance estimates, with one key exception, but we're going to talk about that later on. So what we're going to end up getting is the following. The graph on the right shows you theta and the probability of a correct response conditional on theta, and it gives you this nice S-shaped curve that asymptotes at 0 and 1 in this model. There are other models out there where we'll see the asymptotes change, but again, we'll get to that in a few slides. The logit value itself here, this thing, if we look at what's happening on logits, theta is giving us a linear prediction in logits, right? It's all on the logit scale. It's regression on logits, but we never talk about logits. We talk about probability, so we have to transform it to get us that probability, and that transformation gives us the bendy curve of the line. So, what's that?
Is this the S curve?
The S curve, yeah, monotonic shape, S-shaped curve. It's funny. The S-shaped curve is what we use in logistic regression, but in an we call this an ogive if we use the probit itself. So. Okay, I'm going to stop here. Slide 18. So I will because the next slide talks about kind of how we estimate this. Because now what you're going to see, another big difference between these two models is that CFA was ridiculous. Even though it was really hard to estimate, it was ridiculously easy compared to anything else. And so we have to come up with ways of estimating this that are good, that'll work for a lot of ways. So there's different ways that we see, different methods that we'll see. So we'll get into that next week. All right, everybody, thank you for your time today. If you have questions, just catch me after class. Cash me outside. How about that? All right. Just told my class to cash me outside.
That happens.
That's not good.